I'm putting sections 3.2 and 3.3 together. In 3.2, we'll be doing a lot of what we did at the end of 3.1, but it will be with word problems. So we'll be setting up linear inequalities and then graphing the feasible region. In 3.2, once we have the feasible region, we'll be finding what we're calling the corner points of the feasible region and then testing them in something called an objective function, which we'll talk about shortly. So let's look at this introductory example. It says, suppose the math department at a certain school offers 2 courses, finite math and applied calculus. Each section of finite math can have up to 60 students, and each section of applied calculus can have 50. The department is allowed to offer a total of up to 110 sections. It might be natural to ask how the university could set up a schedule in order to maximize profits. This kind of problem is known as a linear programming problem. So, formal definition of linear programming problem is as follows. A linear programming problem in 2 unknowns, x and y, is one in which we are asked to find the maximum or minimum value of a linear expression, ax plus by, called the objective function, subject to a number of linear constraints of the form cx plus dy either less than or equal to e or greater than or equal to e. The largest or smallest value of the objective function is called the optimal value, and a pair of values x and y that gives the optimal value constitutes an optimal solution. So in our problem up here, the math classes, the constraints were that finite math can only have up to 60 students. So you can't have an unlimited number of students register. That's the constraint on finite math. And for applied calculus, you can only have up to 50. So that would be a constraint. And also that the department is allowed to offer a total of up to 110 sections. So we would have 3 constraints there. And then the objective function here, well, the objective of the university in this scenario is they want to maximize profits. I didn't give us enough information in that paragraph to set up the whole problem, just to identify what is meant by constraints and objective function. So the fundamental theorem of linear programming. And I'm just abbreviating that as LP, so I don't have to write. And it says, if an LP problem has optimal solutions, then at least one of these solutions occurs at a corner point. And when we draw our feasible region, we'll see corner points. So here I have a graph where I've made the feasible region green. And so if we look at that, we would see, okay, where are the corners? Well, one would be right here, one would be right here, and then there, and there. So this particular set would have 4 corner points. And that first bullet point says, if there's an optimal solution, it has to occur at a corner point. There might be more than one optimal solution, but if there is one, it has to be at a corner point. It might happen at more than one. The third bullet point says linear programming problems with bounded, that's really important, non-empty feasible regions always have optimal solutions. So if it's bounded, there is going to be an optimal solution. Remember, this set is bounded. All that means is I can draw a circle around the entire feasible region. So this one would be bounded. So we know it has an optimal solution. It says here, suppose we have the following constraints. So these 2 linear constraints and then those non-negativity constraints I talked about in the last section. We see our feasible region is in the first quadrant. And it says several objective functions of this form. So in general, our objective function is, we'll use P for the letter a lot. It stands for profit. or maybe C, cost, if we're trying to minimize something. How this would work is, well, we would maybe say the profit you make off of, so say X was the number of finite math classes, and you might make $100 profit for every finite math class. So there would be a 1 in front of here for 100. But you make $200 off of every applied calculus course that you offer. So that would be your profit. You make some profit off of finite, some profit off of applied calculus. And then the P could have different values, but P is always going to be a number. Maybe you profit 700, maybe you profit 900, something like that. This part will determine the slope of the line. And so think of if you solve for y and the P is just a number, that's all that's going to change is the y-intercept. So the slope is always going to be the same. If you move the x over, it's negative x and then divide by 2. So your slope is always going to be negative 1/2. You might just have different y-intercepts. So you see that's why I have all these parallel lines going through that region. They all have slope negative 1/2, but they have different y-intercepts. And you want to see when is the last time your line hits the feasible region. So here's the first time you hit the feasible region, and then you move it up a little bit, and you hit the feasible region, you move it up a little bit more, you hit a little bit more, a little bit more, a little bit more. But this one is the last time you would hit the feasible region. And that one, you can see, is going to have the largest y-intercept, which relates to the profit. So the max would occur at this point right here. Okay, so if you increase the y-intercept just a little bit more, now your parallel line wouldn't even hit the feasible region. So we've shown the max will occur at a corner point. What if our profit function was a little bit different? You still made $100 off of finite math, but $1,000 or $1,000 off of applied calculus. Now that's going to change the slope. The slope is going to be negative 1/10, and then you could have all these different numbers for profit, which is going to correspond to the y-intercept. So now you see I have these 4 parallel lines. They all have slope negative 1/10, and we want to look for the last time that line will hit the feasible region. So here it looks like, well, that's the first time we hit the feasible region. You go up a little bit further. Yep, it still hits. Yep, it still hits. And then up here, it should. We want the one that crosses right there. And then if you move the y-intercept up a little bit more, you don't hit the feasible region at all. So again, the max is occurring at a corner point. Okay, so that just illustrates why we only have to focus on corner points to find the max or a min. Steps for solving linear programming problems. The first step is to graph the feasible region, then find the corner points, and I'll talk about how we can use our calculator and matrices to do that. And then substitute the corner points into the objective function to see which gives the biggest value. And then once we do that, find the largest value, that's the optimal solution. So let's do an example. So the first step is to graph the feasible region. So one, I have the non-negativity constraints. So right away, I know my solution has to be in the first quadrant. So I'm just going to cross out everything that's not in the first quadrant. Now, notice I don't have any labels on the x or y axis. That's because I want to figure out first what the x and y intercepts of each of the lines are before I decide on a scale. Okay, so if we focus on the first inequality, remember we graph the corresponding equation, x plus 3y equals 24. And then I'm going to find the x and y intercepts. And remember, to find the x-intercept, we plug in y equals 0. And if I do that, this term is basically gone, so I just get x equals 24. And then for the y-intercept, we plug in x equals 0, so I would have 3y equals 24. And then divide both sides by 3, and I get y equals 8. So you see, we don't want to go up by ones if the x-intercept is 24. So let's go ahead and do line 2, find its intercepts, and then we'll decide on a scale and worry about test points. So for line 2, look at the corresponding equation. Find the x and y intercepts. And remember, for the x, we plug in y equals 0. So we would get 2x equals 18. Divide both sides by 2, and we get x equals 9. And then for the y-intercept, plug in x equals 0, and we would just get y equals 18. Okay, so the biggest x is 24. So I think if I go by 6s, that will work. And the biggest y is 18. I'll go by 4s. 20. There's not like one right answer. So let's plot line 1. So the x is 24, the y is 8. 0, 0 is not on that line, so let's go ahead and use 0, 0 as our test point. One thing I haven't really mentioned is I'm doing solid lines. Everything is less than or equal to, so everything's solid. And when I plug this into the original, I get 0 plus 0 less than or equal to 24, which is true. And 0, 0 is kind of down and to the left. So we want to cross out everything on the opposite side of the line. Okay, so now we're down to that triangle, but we still have line 2 to deal with. So x is 9. 9 would be halfway between 6 and 12. And the y is 18, which would be halfway between 16 and 20. Okay, and then 0, 0 is not on there, so I'll test 0, 0. And I get 0 plus 0 less than or equal to 18, which is true. And 0, 0 is kind of below, so and to the left, so we want to cross out everything up and to the right. And most things are already crossed out. I just need to now cross this part out. So how many corner points does this region have? That's step 2, find the corner points. So the feasible region, remember, is the part that's not shaded in. So it's this right here. And I can see 4 corners. 3 of those 4 corners are really easy to identify. One of them is the origin, 0, 0. One was the x-intercept of line 2, which was 9. So as a point, that's 9, 0. And then this one right here, that was the y-intercept of line 1, which was 0, 8. But then the other one right here, this one is not so obvious. So you can either solve it by hand using substitution or elimination, or we can use our calculator and matrices, and that's the way I'm going to do it. So I'm going to think of this system and making an augmented matrix for that system. Okay, so go to second matrix, edit, and we'll see we'll have 2 rows, and if it's augmented, we'll have 3 columns. And so the top row would be 1, 3, 24. And the second row would be 2, 1, 18. Okay, and then I'll do second quit, and second matrix, math, arrow up to RREF, enter, and then matrix A, second matrix A. Close parentheses, enter. And so we see the solution is x equals 6, y equals 6. So the point 6, 6. And that seems reasonable based on my graph. It does look like the x is 6, and sure, like the y is also 6. So those are our 4 corner points. And then now step 3 is we substitute those into our objective function. And that's the objective function is what we're trying to maximize or minimize. So in this problem, it's right there. Oops. So x plus 2y. So what do we get when we plug 0, 0 into the objective function? Well, we just get 0 plus 0. So p equals 0. What do we get if we plug 9, 0 into the objective function? So 9 plus 2 times 0. So we would just get 9. And then what about 0, 8? So we would get p equals 0 plus 2 times 8, which is 16. And then the last one, 6, 6. So we get p equals 6 plus 2 times 6, which is 12. So 6 plus 12, which is 18. And if we want to find the maximum, we just look at all of those answers and pick the biggest. So the last one we did, that is the biggest. The maximum value is 18. The optimal solution is the 0.66. So this right here, that's the optimal solution. And then just look back on page 1. The largest or smallest value of the objective function is called the optimal value. So 6 is the optimal solution. 18 is the optimal value. Okay, that's that one. Let's look at the next one. So it says find the values of x and y that minimize this function. So this right here, this is our objective function for the following feasible region. What is the minimum function value? Okay, so this time we're trying to minimize. In the last one we were trying to maximize. So they've told us that this right here is the feasible set. So it, as we can see, is not bounded. So there may or may not be a feasible solution or an optimal solution. So what we have to do is identify the corner points. So how many are there? Well, here's one, here's one, here's one. And then it just goes forever in either direction. So this time there are only 3 corner points. One of them I think is easy to identify. They have it labeled for us. This 56,000 is the x and the y is 0. Okay, what about the other 2? Well, the blue line, or the vertical line, says its equation is x equals 20,000. So I know the x-coordinate of that point has to be 20,000. And when I say that point, I mean this one right here, because it is on that vertical line. But what's the y? It looks like it might be 30,000, but I'm not totally sure. The one thing I know is it's on this line right here. I'm just going to call that line 1 for now. And way up here, they give us the equation of that line. So I'm just going to plug 20,000 in for x in that equation, and that will give us the y. And so negative 2 times 20,000 would be negative 40,000 plus 70,000. Yep, that's 30,000. Okay, and then one more corner point. So this one right here. And I'm going to call this other line right here, I'm going to call that line 2. Here's the equation of line 2. So now you can either use substitution, elimination, or your calculator with matrices, which is how I'm going to do it. But you have to get the x's and the y's on the same side before you create the augmented matrix. That's not too bad. You just add the x term to both sides. So I'm just going to go straight to my calculator. And second matrix edit. It's still going to be a 2 by 3. That I'm going to do the line that I have highlighted in blue at the top of the graph. So move the x over, and it would be positive 2. And then the y is 1, and the right-hand side is 70,000. And then the other line, if I move the x over, it would be positive 0.5. And then the y would be 1, and the right-hand side would be 28,000. And then second, quit, and the last thing I have is reduce row echelon form. So just press second, enter, and then enter again. And we get the X is 28,000 and the Y is 14,000. Let's look at our graph and see if that seems reasonable. 28,000, 14,000. Okay, so if I look at this point, yeah, 28,000 seems reasonable. 14,000, yep, that seems reasonable. Okay, and then we need to plug each of those 3 points into the objective function and see which one gives the smallest value. So instead of writing those points all over, I'm just going to label them as A, B, C. So if I plug A into the objective function, I'm just going to do that on my calculator. So the X was 56,000. So 0.01 times 56,000. And then the Y was just 0. So I get 560. Now let's do B. So for B, I see I've made a mistake there. That should be 20,000. I think I said 20,000, but then wrote 2,000. So let's plug in point B. So 0.01 times 20,000 plus 0.016, and the Y was 30,000. And I get 680. And then C, same thing. So if you want, you can type second, enter, and then just type over X and Y. So for point C, the X was 28,000. So just did 28, and the Y was 14,000. And I get 504. And we're looking for the minimum. And this right here was the minimum. All right. This next one is straight from the MyMathLab homework. It says, a local politician has budgeted at most $80,000 for her media campaign. She plans to distribute these funds between TV ads and radio ads. Each 1-minute TV ad is expected to be seen by 20,000 viewers, and each 1-minute radio ad is expected to be heard by 4,000 listeners. Each minute of TV time costs $8,000, and each minute of radio time costs $2,000. She has been advised to use at most 90% of her media campaign budget on television ads. They ask us to fill in the following chart. So let's see. So for 1-minute TV ads, what's the cost? And that is right here, $8,000. So that right there would be $8,000. And the cost for 1-minute radio ads would be $2,000. And then the audience reached for 1-minute TV ads, it says 20,000. And for radio, it's 4,000. And then the amount of money available, that's right in the first sentence, $80,000. They already have the dollar sign, so we just put in. Okay, so that's it for part A, filling in the chart. Part B says let X be the number of minutes of TV ads and Y be the number of minutes of radio ads. Refer to the chart and given inequality that X and Y must satisfy due to the amount of money available. X is the number of minutes of TV ads, and each minute costs $8,000, so that would be 8,000X plus a certain amount of money for radio ads. That was $2,000 per minute, so that would be plus 2,000Y. Now, they don't have to spend all of the money, right? They just have to either spend all of it or stay under budget, and the total amount was $80,000. So that's one of our constraints. Part C says, give the inequality that X must satisfy due to the limitation on the amount of money to be spent on TV ads. That's not from the table. That's just from this sentence right here. Use at most 90% of her media campaign budget on television ads. First of all, what is 90% of that budget? So we just want to do 80,000 times 0.90. And you can do that on your calculator, and you should get 72,000. Okay, and now every minute of TV ads costs $8,000, so we need 8,000x to be less than or equal to 72,000. Because they say at most, which means you could be under. That's fine, just don't go over. And then to get x by itself, divide both sides by 8,000, and you'll get x less than or equal to 9. So that's the answer for part C. And then part D says give an expression for the, also give the inequalities x and y must satisfy because x and y cannot be negative. Those are our non-negativity constraints. X greater than or equal to 0, y greater than or equal to 0. Now part D. Give an expression for the audience reached by X minutes of TV ads and Y minutes of radio ads. So I'll just say I'll call that A for audience. This is our objective function. She wants to reach the largest amount of people while staying within her budget. So how many people for TV? 20,000 per minute. So it would be 20,000x plus how many by radio? 4,000. So it would be 4,000y. So like I said, this right here is our objective function. Okay, and then part E, it just asks us to graph the feasible set. So I need to find, well, one, I know it's going to be in the first quadrant, so I can cross out everything that's not in the first quadrant. But then for our other constraints, I want to find the x and y intercepts so I can decide on a scale to use. And how many do we have? We have 1, 2, and then the non-negativity I've already taken care of. Okay, so for 1, I want to find the x and y intercepts. First, we'll change to an equation. So it would be 8,000x plus 2,000y equals 80,000. And then we'll find the x and y intercepts. So remember, for the x-intercept, y equals 0. So we would get 8,000x equals 80,000. And then divide both sides by 8,000. And we get x equals 10. And then for the y-intercept, we let x equals 0. So we would get 2,000y equals 80,000. And then divide both sides by 2,000. And we get y equals 40. So I know my y's at least have to go up to 40. And then the second one is just x less than or equal to 9. So that's just a vertical line at x equals 9. Okay, so the largest x I need is 10, and the largest y I need is 40. So 2, 4, I think I can go by 2's on the x, 10, and I think you can go by 8's, I guess, on the y. You could also go by 10 if you want. And the second line, that one's easier. I'm just going to do that one right away. The x equals 9, the vertical line. And it was x less than or equal to 9. 0, 0 is not on the point, so I'll test 0, 0. So I get 0 less than or equal to 9, which is true. And 0 is to the left, so we want to cross out everything on the opposite side. So cross out everything over here. And then for line 1, the x-intercept was 10 and the y-intercept was 40. And 0, 0 is not on that line. So we can use 0, 0 as our test point. And if I do that, I would get 0 plus 0 less than or equal to 80,000, which is true. And 0, 0 is down and to the left, so we cross out everything up and to the right. And so just this part right here, I'm going to abbreviate, is the feasible set or feasible region. They don't ask us to find corner points, but if they did, there would be 4 of them. You get this one, this one, this one, and this one.